Okay, so this is the second video in our series on transformations of functions, and in the first video we looked at transformations from a sort of function notation perspective. So really taking what you know about transformations and exploring that in a little bit more depth. But now what we want to do is actually take two really big steps backwards and go back to actually the beginning of where the transformations start. So we want to look at how each transformation affects the coordinates of the points on each graph, and then look how that change affects the equation of the graph. So what we've done up until this point is that you've just jumped in at looking at the equation straight away and seeing, all right, a -2 there means right by 2. Oh, right, a 2 there means dilated by 2 from the x-axis. But what we want to do is see how, if we dilate by 2 from the x-axis, what happens to every point on the graph. How do we then take that information and apply it to the rule to come up with the functions that we are somewhat familiar with? And it's important to take this step back because, as I said in the previous video, I find that many students don't have strong enough function notation skills and algebra skills to be able to actually effectively and accurately work from function notation when it comes to transformations. And being able to take this step backwards actually gives you more tools to be able to, do a few more algebraic steps, but the consequence is that it's a much more reliable process for you getting to the right answer. So let's start with sort of where we're at. So we know we've talked about in the previous video that a transformation is a mapping from R2 to R2, which means that every point on the Cartesian plane is mapped to another unique point on the Cartesian plane via that transformation. So if you were translating to the up by 5, you would add 5 onto the y coordinate, and every single point you're adding 5 onto its y coordinate, and you're transforming all of the points on the Cartesian plane in that manner. And that results in the graph being in a different place. So for example, the point 0, 0 may be mapped to the point 2, 3, and we would write that in this way. 0, 0 is mapped to the point 2, 3. More generally, we would start to talk about transformations in this way. If xy maps to xy plus 3, so no change to the x coordinate, but adding 3 onto the y coordinate, we should be able to interpret what that means as a transformation. So if we add 3 onto every y coordinate, all we're doing is translating the graph up by 3. So this is a translation up by 3 units. The transformed point is referred to as the image of the original point. We introduced that word in the previous video, and we would use this notation to talk about the transformed point, so x dash, y dash. So in this example up here, we would say that x dash is x and y dash is y plus 3. The image of y is y plus 3. Okay. Similarly, the rule of the transformed function is referred to as the image of the original function, but we wouldn't use f dash to talk about the image function because obviously f dash is already the notation we use for derivative. You could call it f1 of x or f star of x or a whole other function name g of x. There's no standard notation. I'd probably just revert to y equals for the image, but up to you. So once we've got our knowledge of our basic functions, coupled with a really good sound understanding of our transformations, it's really going to allow you a lot of flexibility when working with functions and sketching lots of different graph types. Even things you might not be particularly familiar with. You could be given a shape, you've never seen it before, but you should then be able to sketch f of x plus 2, or f of x minus 3, or 2 times f of x, or whatever it might be, on the basis of your knowledge of transformations. Okay, so in the previous section we talked about the 3 different types of transformations: dilations, which we can do from the x or from the y-axis; reflections, which can be in the x or in the y-axis; translations, which could be left or right or up or down. Okay, and we looked at those from the function notation perspective. So we looked at the fact that if we have f of x and 3 times f of x, we're dilating f of x by a factor of 3 from the x-axis, which means stretching in this direction, multiplying all the y values by 3. So if we talk about that as what's happening to every point xy becomes the point x3y. We multiply the y coordinate by 3. Okay, so this is what happens to every point on the graph and as a result, this is what happens to the equation of that graph. It's important that we make a distinction between those two different things. Okay. Over here on the right, if we're dilating from the y-axis, so here we've got the graph of f of half x, okay, which is f of x after a dilation of 2 from the y-axis. So we're doubling all the coordinates this way, okay, which means it's the x values that are being doubled. So every point xy becomes the point 2 times xy. And again, we want to be able to make this distinction between this is what's happening to every single point, and when we apply it to the equation, this is what happens. Okay. Reflection in the x-axis. We know that when we reflect in the x-axis, we multiply every y value by -1. Okay. And so therefore each point, the y value is multiplied by -1. X values coordinates stay the same, but the y coordinate is multiplied by -1. And again, we want to be able to understand that when this happens to every point on the graph, this is what happens to the equation of that graph. We end up with negative f of x. When we reflect in the y-axis, each point gets reflected in the y-axis, which means its x coordinate is being multiplied by -1. Okay, and so if we multiply all the x coordinates by -1, this is what happens to every point. If the point was at xy, it becomes negative xy. And again, we want to be able to look at if this is what happens to every point on the graph, when we apply that to the rule for the graph, the result is that. Okay. Translations in the direction of the x-axis, that is left or right. Okay. If we were to have a look at this function here, we've got f of x plus 2, which is a translation to the left by 2. Okay. We've moved everything to the left by 2, which means in terms of what happens to each point, we are subtracting from the x coordinate. This is the point 3,9. This is the point 1,9. We've subtracted 2 from the x coordinate to get the new coordinates. Okay, so if we have, generally speaking, the point xy, when we translate to the left by 2, we're going to the left by 2, so we're subtracting 2 from the x value, so we get x minus 2y. And again, what we want to look at is how, if this is what happens to every point, the result in the equation ends up being this. Okay, and this is one of those points where it's really important to understand the distinction between the point and the equation. Okay, two different representations. And finally, translating up or down or in the direction of the y-axis. If we translate the graph up by 5, we get we're looking at this equation here, f of x plus 5, which translates the graph up by 5. Every single point has moved up by 5, so we're adding 5 onto the y coordinates. If the original point was xy, the transformed point is xy plus 5. And again, we want to look at if this is what's happening to every point, the result when we apply it to the equation is going to be that. Okay. Alright, so summary of our transformations of a point. So if we dilate by a factor of a from the x-axis, we could also describe that as dilating by a factor of a parallel to the y-axis. So it's really important, again, that you can be flexible about the words and really think about, get some hand motions going. If I'm from the x-axis, that's an up and down kind of movement. Similarly, if it's parallel to the y-axis, that's also an up and down kind of movement, right? So you want to be able to understand, not just looking for the words x or y, because it depends on, is it from that axis or parallel to that axis or in the direction of that axis? So really thinking clearly about what the words mean. So if we dilate by a factor of a from the x-axis, it's the y coordinates that are being multiplied by a. So the point xy becomes the point xay. Okay. If we dilate by a factor of n from the y-axis, which could also be described as dilating by a factor of n parallel to the x-axis, it is the x coordinates that are changing, and we're dilating by a factor of n. The x coordinates are being multiplied by n. Okay, again, this is one of those ones where I know it ends up looking backwards in the equation. When we then look at the function, we'll see that y equals f of x becomes y equals f of x on n. These are saying the same thing. Okay, they're not contradicting each other. It's really important. what happens to the point is that the x coordinate gets multiplied by n. Okay, that stretches it out by a factor of n, which is what we're trying to do. Okay, when we then look at what that looks like in the equation, it ends up looking like this. Okay, and we need to know when we see the function, we interpret that as 1 on n times x is a dilation by a factor of n from the x-axis, because we take the reciprocal from the function notation. Alright, if we're reflecting in the x-axis, it's the y coordinates that become negative, so x negative y. If we're reflecting in the y-axis, it's the x coordinates that become negative, negative x, y. If we're translating up by k units, we're adding k onto the y values. If we're translating down by k units, we're subtracting k from the y values. If we're translating right by h units, we are adding h onto the x coordinates. Again, when we then look at how this applies to the function, f of x will become f of x minus h. Okay, these are not contradicting each other. These are the same thing. If every point gets moved to the right, we're adding. Okay, it's as simple as this point. If I want to move it to the right, its x coordinate is getting bigger. Okay, we're adding onto its x coordinate to move it to the right. When we then look at how this, when we apply this to the actual rule, we get this particular function. Okay, and we'll see that process in a minute. And when we translate to the left by h units, x minus h, we're going to the left, we have a point, we want to move it this way, its x coordinate, we're subtracting from its x coordinate. Okay. Alright, so I've grouped them specifically because these transformations in this column all affect the y coordinate, whereas these transformations in this column all affect the x coordinate. It's really important that when we come to starting to combine the transformations together, the transformations affecting the y coordinates are not going to impact on those affecting the x coordinates. So if you've got two different transformations, one affects the x coordinates, one affects the y coordinates, it doesn't matter what order they happen in. They're not interfering with each other. The issues will be when you've got more than one transformation affecting the same coordinate. You do need to be careful about thinking about the order that they are being applied in, because if we add k onto the y values and then multiply by -1, that's different to multiplying by -1 and then adding k. So the order becomes important when we are within the same coordinate. Okay, so what we want to now look at is how, thinking about the point first, how do we then apply that to a rule? Okay, so we're going to do a really simple one, which is to just determine the rule for the image when the graph of this parabola is dilated by a factor of 3 from the x-axis. Now, we already know that if we dilate by a factor of 3 from the x-axis, we're going to expect to get 3 times f of x, which means 3 times all of that. Okay, but let's see how we actually go about doing that. So we think about the point first. If it's a dilation by a factor of 3 from the x-axis, I'm going to get rid of that in a minute. We know what we're expecting our answer to be though. Dilation by a factor of 3 from the x-axis means every point x, y, the y coordinates are being multiplied by 3. Okay. Now this is our image point. This is the image of x and the image of y. Okay. And so from that we get two small equations. The image of x is x and the image of y is 3 times y. Now we want to take this information and we want to apply it to this rule. Okay. This rule has x and y in it, not x dash and y dash. So we need to make x and y the subject of these two equations. So this is pretty trivial. X is just equal to x dash. Here, y is equal to y dash divided by 3. And now we're going to be able to replace y with y dash over 3 and x with x dash. Okay, that doesn't make too much difference, but the y does. Alright, so now we know that y equals x squared minus 6x plus 1 becomes y dash over 3 equals, just put it in brackets because it's a bit messy with the dashes and the squares, x dash squared minus 6 times x dash plus 1. Now, once you've made the substitution, you can stop calling them x dash and y dash. There's no problem with that. And so we've got y on 3 equals x squared minus 6x plus 1, and then we just need to multiply everything by 3, which means that y equals 3 times all of that which is what we knew would happen when we do a dilation by a factor of 3 from the x-axis. We multiply the whole function by 3, and so we get 3x squared minus 18x plus 3 is our rule for the image after a dilation by a factor of 3 from the x-axis. Now, this is where you want to start to be able to be flexible. If you're just applying one simple transformation to a function, I wouldn't suggest that you have to go through this slightly lengthier process. But the minute you start to combine transformations, this is going to be far more accurate for the vast majority of you, okay? And there's a few more algebraic steps, but they're very, very simple algebra. It's simple rearrangement of linear expressions, simple substitution, and then just making y the subject. Okay, so let's generalize these things and just establish that this is still consistent with what we looked at in the previous video. So the general cases can be established by applying this process to a function y equals f of x, so a general function rather than a specific function. So for this example, we want to determine the rule of the image when the graph of y equals f of x is, in part A, dilated by a factor of n from the y-axis. Okay, so if we dilate by n from the y-axis, it is the x coordinates that get multiplied by n, okay? This is our image of x and our image of y, and so we get two small equations which say that the image of x is n times x, and the image of y is y. Now, we want to substitute into this rule here, which has x and y in it. So we want to make x and y, not x dash and y dash, the subject of our equations. So x equals x dash on n, y equals y dash. And now we can substitute. So y equals f of x becomes, we replace y with y dash equals, and we replace x with x dash on n, okay? And we can lose the dashes once we're done with the substitution. So we find that the image is y equals f of x on n. So if this happens to every point, this is what that ends up looking like in the equation. Okay, completely consistent with what we saw in the previous video. If we reflect in the x-axis, every point x, y, the y coordinate becomes negative. And so this is the image of x and this is the image of y, and we've got then two little equations. The image of x is just equal to x, and the image of y is equal to negative y. We need to have x and y as the subject so that we can substitute into this. So x is equal to x dash, y is equal to negative y dash, and now we can substitute. So y equals f of x becomes, start replacing y with negative y dash equals f, and replacing x with x dash. Okay, making y the subject, and we can lose the dashes now that we've done the substitution. So y equals negative f of x is the image, image of the function y equals f of x after we have reflected in the x-axis. So again, completely consistent with what we've seen previously. If this is what happens to the point, this is what that ends up looking like in the function. Okay. Translation by h units to the right. So if we think about our point, we start with x, y, we translate it to the right, means we're going to be adding on to the x value. We want to take a point and move it to the right, we need to add, okay? And then this is the image of x, and this is the image of y, okay? So x dash equals x plus h, y dash equals y. So x, we want to make x and y the subject because we want to substitute into this rule which has x and y in it. So x equals x dash minus h, and that's where that plus turns into a minus, and y equals y dash, and now we can substitute y equals f of x, replacing y with y dash, and x with x dash minus h. And so we can lose our dashes. Y equals f of x minus h is the image of the function. So if that is what happens to the point, if you add a value onto all the x coordinates, when you apply that to the function, that is what it ends up looking like. Okay. And the final one, translating k units up. So if we take a point x, y, and we translate it up by k units, we're adding k onto all the y values. Okay. This is our image of x, and this is the image of y. So we get that x dash is equal to x, and y dash is equal to y plus k. And then we want to substitute into this rule, which has x and y in it. So we need x and y to be the subject. X is x dash, and y is y dash minus k. And then we find that y equals f of x will become, we replace y with y dash minus k, and we replace x with x dash. And we can lose the dashes and make y the subject. So it is f of x plus k. Okay, so you can see here in this last example why when we add onto the y values, okay, in the process when we make x and y the subject instead of x dash and y dash the subject, we create the inverse operation. So we create a minus k here. But then when it's affecting the y coordinate, when we substitute that into our rule, because then we make y the subject again, we undo those things and we end up with it being a plus k again. However, when it affects the x coordinate, you're adding onto all the x coordinates, you rearrange to make x the subject, and you create all the inverse operations. So now instead of it being plus h, it's minus h. Then when you substitute that into the rule, if it's about the x coordinate, in order to make y the subject, you don't end up undoing all those things again. So it still remains in the function looking opposite to what it should. The same thing happened up here with the dilation from the y-axis. We multiply all the x values by a number, but then when we rearrange to make x the subject, we create the inverse operation, which is to divide by that number. And then when we substitute into the function, when we go to make y the subject, we don't end up undoing those things again. Okay, whereas here, up here, when we put this into when we did the dilation from the x-axis and we substitute this into the equation, we then, when we make y the subject, we multiplied everything by 3 again. So it went back to looking like 3 times the function. So the things inside the function, because they don't get undone when we rearrange when we make y the subject at the end, they still remain as the inverse operations. Whereas things that affect the y coordinate, we rearrange to make y the subject, we substitute into the equation the sort of inverse operation, but then when we make y the subject, we uninverse it, if you like. We end up with it as a plus k again in the equation. Okay. So generally speaking, here are all our summary of all our transformations. So if we are dilating by a factor of a from the x-axis, we're multiplying all the y coordinates by a. That's what happens to every point. And when we apply that into the function, we end up with y equals a times f of x. When we're dilating by a factor of, sorry, that's inconsistent. Let's make that n. When we're dilating by a factor of n from the y-axis, we're multiplying all of the y values. Sorry. All of the x values by n, and when we apply that into the function, it looks like y equals f of x on n. Okay, and we can see that consistently. Reflection in the x-axis is multiplying the y values by -1, which is negative f of x. Reflection in the y-axis is multiplying all the x coordinates by -1, which results in the equation as being f of negative x. Translating right by h, we add h onto all the x coordinates. When we apply that into the function, we get f of x minus h. Similarly, translating left, we're subtracting from all the x coordinates. When we apply that into the function, we get f of x plus h. Translating up by k, we're adding k onto all the y values. We apply that into the function, we get f of x plus k, and down f of x minus k. Okay, so now we want to be able to actually combine more than one transformation. Okay. And the same process is used whether we imply one or a sequence of 2, 3, 4, 5, 20 transformations. And that's where this process becomes more flexible. For just one transformation, your function notation is probably good enough to just write down the answer. But if it's more than one, it could be up to 20. It's no harder than it being just one transformation. Okay, it's pretty much the same thing. You've got to generate what happens to the point, and then the process is identical, whether it's one transformation or 10 transformations. Okay, so let's work through these examples. Determine the rule for the image when the graph of y equals 1 on x is reflected in the reflected in the y-axis and then translated 4 units to the right. Okay, so we want to build up what happens to the point. So if we start with a point xy, and the first thing we do is reflect it in the y-axis, okay, we are going to make its x coordinates negative. Then we translate it 4 units to the right, which means we now take this existing point, okay, so just pretend that that is x and y, and we're going to add 4 onto the x coordinate. So we're not changing the existing x coordinate, it is negative x, we're adding 4 onto it, okay. So we're going to have, negative x and then we add on 4, okay. So it is simply just building up those operations. So we multiply the x coordinate by -1 and then we add 4 to the x coordinate, and this is where we end up. So now our process is the same. This is the image of x, this is the image of y. That gives us two little equations. X dash equals negative x plus 4 and y dash equals y. But then we want to be able to apply these transformations to this rule up here, and so we want to make x and y the subject. So that means that I'm going to add x and take away negative x. So, well, you could do it a couple of ways. If we take away 4, x dash minus 4 equals negative x, but then we multiply everything by -1, we get 4 minus negative x, or negative x plus 4. And y is just y dash. And now we can apply it to the rule. So y equals 1 on x is going to become, we replace y with y dash, and we replace x with 4 minus x dash. So therefore the image is y equals 1 on 4 minus x dash, 4 minus x, sorry. No work to be done to make y the subject. So that is the rule after we reflect in the y-axis and then translate 4 units to the right. Let's have a look at part B, where we're going to do those same two transformations but do them in the reverse order. We're going to translate 4 units to the right and then reflect in the y-axis. So again, let's build up what happens to the point first. We start with the point xy. The first thing is to translate 4 units to the right. So we're adding 4 onto the x coordinate. Now, that is the x coordinate, and that is the y coordinate, and we do the next thing to that is the whole x coordinate. So if we then want to reflect in the y-axis, which is to multiply the x coordinates by -1, we're going to multiply the entire existing x coordinate by -1. Okay, so it's going to become negative x plus 4 y. Okay, so we've added 4 onto the x coordinates, we've multiplied the x coordinates by -1. Okay, so we could tidy that up if we want. That's negative x minus 4y, or you can leave it as it is, it doesn't really matter. In fact, I might leave it as it is. So this is the image of x and this is the image of y. We now have our two little equations. The image of x is negative x plus 4. The image of y is just y. We want to make x and y the subject, so we can substitute into the hyperbola. So I'm going to multiply both sides by -1, so negative x dash equals x plus 4, and take away 4, x equals negative x dash, take away 4, and y just equals y dash. Alright, so y equals 1 on x is our function, replacing y with y dash, and replacing x with negative x dash minus 4. And so therefore the image is 1 over negative x minus 4, which you could alternatively write as, you don't have to, but you could alternatively just write that as negative 1 over x plus 4, just factoring the negative out of that whole denominator. Okay, but the point is that it's not the same as this one up here. You did the same two transformations in a different order. Okay, that's where you've got to be careful about building them up. At each step, that whole thing is the x coordinate, that whole thing is the y coordinate. You do the next step to that whole coordinate. Okay. Alright, let's have a go at another example. Find the rule of the image when the graph of y equals square root of x is translated 3 units to the left, then reflected in the x-axis, then dilated by a factor of 4 from the y-axis. Okay, let's start with our point, xy. Translated 3 units to the left. Okay, so we're subtracting from the x coordinate. Okay, if we're taking a point and moving it 3 units to the left, if this was xy, this is now x minus 3y. Okay. Then we're reflected in the x-axis, so that means that we multiply the y coordinates by -1. So x minus 3, and that existing y coordinate times -1, so it's just -y. And then we dilate by a factor of 4 from the y-axis. So 4 from the y-axis, we're multiplying the x coordinates by 4. We're stretching out this way times 4. It's the x coordinates that are being multiplied by 4. And so we're taking this whole existing x coordinate and multiplying that by 4. Okay. You can expand that out if you want. You can do that later if you need. This is x dash and this is y dash. So the image of x is 4 times x minus 3, which you might choose to write as 4x minus 12. Up to you. And the image of y is negative y. Okay. So we want to make x and y the subject, so we can substitute into our rule, y equals root x. So we're going to add 12, x dash plus 12 equals 4x, and divide by 4. So x equals x dash plus 12 on 4. Or if you hadn't expanded out the brackets at the beginning, when you did the rearrangement, you would have ended up with x dash on 4 plus 3, which is the same. Okay. So whichever, that's no different. And then here, this is just going to be y equals negative y dash. Alright, so our original rule is y equals root x. We replace the y's with negative y dash, and we replace the x's with x dash plus 12 all over 4, or with this. The whole thing goes under the square root. And then lastly, we just want to make y the subject, which is just to multiply both sides by negative 1. I'm going to lose the dashes in that process as well. So it's just going to be negative square root of x plus 12 all over 4. That is the image of this function after we have translated 3 units to the left, then reflected in the x-axis, and then dilated by a factor of 4. You could also write this instead as a quarter times x plus 12 if you prefer. This could also be a quarter times x plus 12, that's fine. You could then simplify this answer if you want as negative root x plus 12 over 2, but it's not necessary to do that. It's fine as it is. Up to you. I'll write that down though as an option. Okay, example 5, the last one here. So find the rule and sketch the graph of the image. So we're going to sketch a graph after we've done it, of y equals x to the power of 4 after dilation from the x-axis by a factor of 2, translation to the left 6 units, and translation in the positive y direction by 3 units. Now this is a pretty standard sequence of transformations because it's dilation, there's no reflection, and then it's dilations and then the translations. So it's going to end up pretty much in turning point form. A dilation from the x-axis, a translation left or right, and a translation up. So it really is going to be dilation by a factor of 2, translation to the left by 6, and translation up by 3. That should be our final answer. So I'm not saying you need to overly complicate things if it's a nice simple sequence of transformations or a nice simple answer. I will go through the process here so you can see that it does result in the right answer, but I want you to practice this process, but equally then once you're comfortable with both processes, develop some flexibility about what's going to be the most efficient method. Okay. So if we build up our point, we've got the point x, y. We dilate by a factor of 2 from the x-axis, which means the y coordinates are being doubled. Then we translate to the left by 6. So we take our existing x coordinate and subtract 6 from it. And then we translate up by 3. Positive direction of the positive y direction is up. And so we take the existing y coordinate and add 3 to it. So x minus 6 and 2y plus 3. Okay. So this is our image of x, this is our image of y. The image of x is equal to x minus 6, which means x equals the image of x plus 6. And the image of y is equal to 2y plus 3. And so 2y is image of y minus 3. And so y is image of y minus 3 all over 2. Okay. So now we can apply to our rule. It's y equals x to the power of 4. We replace y with y dash minus 3 over 2, and we replace x with x dash plus 6. And now we can lose the dashes and rearrange to make y the subject. So we're going to double both sides. It's 2 times x plus 6 on 4, and we're going to add 3. So we get 2 times x plus 6 to the power of 4 plus 3. And that is the image of the original quartic after that sequence of transformations. Okay, so the practice today is again from a worksheet at the back of your booklet, applying transformations using first principles. So I want you to practice with this process, just so that you are comfortable with both processes, and then you're in a position to be able to make good decisions. Okay, whoops, I just finished recording and then realised that this last example had asked us to actually sketch the graph. So now that we've come up with the rule for the image after that, and also that we know all the transformations, so we're dilating from the x-axis by a factor of 2, that doesn't affect too much about how you draw it, that'll come into the calculations. So you've got a quartic function dilated by a factor of 2, it's going to be taller and thinner, translating to the left by 6 and up by 3, means that it's going to have its turning point at negative 6, 3, and we'll draw it up here and we'll calculate the y-intercept. So it's definitely not going to cross the x-axis, given what we know. So we're going to have, let's see if we've got room down here, yes we do. Okay, so we want to calculate our y-intercept. So our turning point is at negative 6, 3. Our y-intercept, given the shape, there won't be any x-intercepts. It's a happy-shaped quartic with a turning point above the x-axis, so it won't cross the x-axis. So we just need the y-intercept, 2 times 6 to the power of 4 plus 3. That is 2 times, now 6 squared is 36, so it's 36 times 36, or 6 cubed is 216, and then we have to times that by 6 again. 200 times 6 is 1200. 10 times 6 is 60, and 6 times 6 is 36, so that's 60 and 36 is 96, so 1296. You do need to be able to do that level of number work in your head. I'm not expecting you to know by rote what 6 to the power of 4 is, but you still should be able to think it through and work it out, even if it means doing 36 times 36, and 6 6s are 36, and 6 3s are 18, plus 3 is 21, and carry the 0, and 3 6s are 18, and 3 3s are 9, plus 1 is 10, and so you get 6, 9, 2, 1. Okay. However you do it, you have to have a way to be able to do that level of number work. Then we want to double that, so if we think about, I might think about, this is close to 1300. 2 lots of 1300 is 2600, but it's actually 4 less than 1300, so this is 8 too many, so it has to be 2592. So 2592. Other ways you could do that: 2 times 1000 is 2000, 2 times 200 is 400, so 2400 plus 2 lots of 96, and 2 lots of 96 is 192, and so we get 2592 plus 3, and then so we've got 2595. So really big y-intercept, which makes sense given both the dilation and the quiet, and the fact that you've moved to the left quite a bit. You know, you've moved away over here, so it means your y-axis is going to be way up there. So let's try and, so we're going to go with negative 6, 3, and we're just going to indicate, it's not going to be perfect scale obviously, but we want to aim to cross as high up here as we can. I'm going to aim for a similar starting point over here, sort of square shaped, because it's a quartic, not a parabola, square based I meant. 0, 2, 5, 9, 5. Turning point is at negative 6, 3. Okay, at least 2 points including the turning point is sufficient, and we are done. Right, so now you can go on to the worksheet.